Hello and welcome to the video lecture series brought to you by Saitm Institute of Technology and Management. My name is Ravinder. I am an assistant professor with the TC department, and in this particular video lecture series we are discussing the subject of data structures 2, or as you know it, advanced data structures. For past few lectures we are discussing a very important data structure called graphs, and I think we are at the end of this particular topic. We will be discussing last few topics in this and upcoming two lectures. And in today's lecture, broadly, we are going to discuss a very important algorithm for finding out the shortest path in weighted graphs. Okay, we haven't discussed what the weighted graphs can be. So we'll discuss the weighted graphs first, and after that we'll try to find out the shortest distance between the two vertices. And the algorithm to find the shortest distance between two vertices is called as Yastra's algorithm, as I have written here. Its name hard to pronounce, but doesn't matter. So first thing first, before discussing this particular algorithm and the concept of weighted graphs, let us go back to the last lecture. I think we have left with the algorithmic description of topological sorting. We have seen how a topological sort uh, achieves achieves the sorting of the what I can say, the traversing technique of going through the lags directed acyclic graphs, but we haven't seen its algorithmic description. So let's quickly see its algorithmic description, and after that I'll come back to the main topic of discussion for this particular lecture. Okay. Okay. Now we have seen what we have to do in topological sorting. So I will quickly remind you what we have discussed in the last lecture. For a particular problem, first of all, we have to identify which of the following vertices or vertex has an in degree of 0, and we can start with any one of them. And after starting with after choosing any one of the in degree 0 vertex, we have to mark it as enumerated, and then we have to delete this particular vertex. If I have chosen this particular vertex called the vertex 1, uh, the condition is that it must be of in degree 0, and after that I have identified it, I must mark it as enumerated, and then I have to delete this. So in next, okay, now this is what I've seen. I have marked 1 as enumerated here in this particular array, and I have also deleted all the edges that are being connected or being linked to the first vertex or the vertex number 1. And in this way and now again in this particular step I will again calculate the in degree of each and every vertex. As you can see, the in degrees of these vertices called 3, 4, 5, 2 are different from the next step, because after the deletion of the initial and the first vertex called the vertex number 1, the in degrees must have been changed. So I have calculated them again. Then again I will look out for the vertices which have an in degree of 0, and I will try to choose one of them, and then I will enumerate that particular vertex and will mark it as enumerated in this particular array, and I will delete that particular vertex after that. Okay, and then again in the next step I will again try to calculate the in degrees of all the vertices in the particular problem. So this is how we'll go on. Okay, so you until now you must have an concrete idea of what we are trying to do here. So quickly I will go through the algorithmic details. Okay. Now this is the algorithmic representation of the topological sorting or ordering, as you can call it. As you can see, this particular topological ordering algorithm consists of two parts, the first part and the second part. The first part is mainly for calculating the initial in degrees. Let me again reiterate that, for calculating the initial in degrees of all the vertices in a particular graphical DAG or directed acyclic graph, that is a particular problem. So what I'm trying to say is, At this point of time, when we haven't enumerated any of the, let's say, vertex, and we haven't deleted any of the vertex, so at this point of time, for finding out the source of source for starting out the topological sorting, as I have told you just a few minutes ago, that we have to find out the vertices which have an degree of 0. Okay, so for that, first you have to calculate the in degrees of each and every vertex. So that first part in our algorithmic representation actually find out the in degree of each and every node or vertex in the problem. Okay. Okay. So this particular function which describes the topological ordering will have an input as an argument, as an argument as the graph G. Okay, now in this G we will have several vertices and edges. Now for each combination of vertices, that is let's say I comma j, where I is one vertex and j is the other vertex, and there must be a relation from I towards j. Okay, I think you must have been familiar with the directed A's like cyclic graphs or till now, so you must have understand what I'm trying to say with an edge or a relation I comma j. Now for every I that is linked from 1 to n, and n be the total number of let's say vertices in this particular G, we will first initiate the in degree of a particular I equal to 0, as we do not know how many connections it have. So we just have to initialize the initial value of in degree equal to 0 of each and every vertex, and then we will try to find out if the in degree is different from 0 or not. So for every I which has a combination of j, and it might be from 1 to n, so you can say that let's say in this particular problem you can say this one is I, and then I have to then I have to find out all the possible combinations of this particular I with all the j's available, and those j's will be ranging from 1 to n. Okay, so the combinations will be 1 comma 1, 1 comma 3, 1 comma 4, 1 comma 5, 1 comma 2, 1 comma 6, 1 comma 7, 1 comma 8. So if you have an adjacency matrix, so you have to look how many of these combinations are valued as 1, and if they are valued as 1, you can easily conclude that yes, there is a valid edge between these two vertices. So in that way, we'll have to go through each and every row of your adjacency matrix first. Okay, so for every possible j, if that combination holds the value of 1 in your adjacency matrix, then you can update the in degree of 1 to the initial value plus the h, and this value must be 1 in your adjacency matrix. So this is what I am saying. So if let's suppose the value of I is 1 in this particular place, so initially I will let's say initially I will see that how many sorry initially I will set the in degree equal to 1, and then I will see in the adjacency matrix how many of the combinations, that is from particular j towards I, has value 1. Let me remind you again that we are calculating the in degree, not simple degree. So only those edges will be counted as 1 which have a possible combination which amounts from this, which are coming inside the particular edge. Okay, so for this particular node or vertex, we have no edges that are coming inside, so the complete row will be 0 practically. So the in degree will remain 0. But for this particular node, let's say I has a value of this, so we'll try to see for every possible j if we have possible coming edge for towards this particular vertex called third, and if it amounts equal to 1, then we can update the in degree. So initially if it has an in degree of 0, as we have initialized it, We will go through the adjacency matrix and see how many edges are coming in. We have two edges that are coming in from one and from two vertex. So in adjacency matrix, these two combinations, that is 1 3 and 2 3, must be equal to 1. So the initial end degree, which is equal to 0, will be updated twice, that is uh, for this particular combination and this particular combination. So the end degree of this particular vertex called 3 in the end will be equal to 2. So this is what we are trying to do here in the first block. We are trying to calculate the end degree of each and every vertex in the graph. Now in the second vertex, actually we have started the topological sorting. Okay, now in this case, down here, the edge will be j comma I, not I comma j. Okay. So we will choose first a particular vertex j, which has an end degree of 0. And that is, as you can recall it, that is how we have started the topological ordering. We first have to see how many of the vertices have an end degree of 0, and then we can choose one out of them. So I have chosen a vertex j which has an end degree of 0. Now this particular end degree of j is equal to 0 has been calculated by this particular half of the algorithm. Now as we have selected that particular j, now we will enumerate it. Enumerate means we will complete the whatever be the task there assigned to us, as we can link it to many day-to-day problems. So there must be a task there. Now I will delete. Now what I have to do is I have to delete this particular vertex from the graph. Now we will not actually delete it from the graph, but all we have to do is I will assign an end degree equal to -1. I will assign an end degree equal to -1 to this particular vertex, and this practically means that this particular end degree, this particular vertex j, has been already enumerated and removed, has been already enumerated and removed from the problem. Okay, so this is what it signifies. Now, after the removal, as you can recall, we have calculated the end degrees of each and every remaining vertices again. So this is what we'll do for every k that amounts from 1 to n. I will first say if there is a possible combination that leads from j to k. Okay, and in adjacency matrix, if that possible combination amounts equal to 1, and if in the adjacency matrix this possible combination has a value of 1, it means that there is an edge which is coming inside k from the vertex g. Okay, so what I am trying to say here is that after that I have deleted this particular vertex here, after its enumeration, I have to calculate the end degree of this particular vertex, this particular vertex, and this particular vertex. For all other vertices, there will be no difference in the end degrees because they are not connected or have a relationship with the first vertex whatsoever. So for these two, how will I find out that if there is a possible edge? All I have to do is, for in adjacency matrix, for the combination, let's say j k is equal to 1, it means there is a possible edge that is coming from 1 to 3. Then all I have to do is I have to recalculate the end degree of this particular vertex k, and I have to decrement it by -1. Okay, so what we have done here is, let's suppose this particular vertex 3 has an end degree of 2 initially, and when I have deleted this particular vertex, and yes, there in the adjacency matrix, you will see that the particular data point a j comma k has equal to 1 because there is a valid edge coming from 1 to 3rd. Then in the next step, when I will again recalculate the end degree, I will decrement the end degree by -1. So here the vertex 3rd has end degree of 2, and in this point the end degree is equal to -1. So that 1 that has been subtracted from the end degree of 3rd is actually amounts to the one vertex that is here, and it has a valid edge from this particular vertex to this particular vertex. So this is what has been happening here. If you find yourself confused while I am telling you all this, all you have to do is just recall these past 6 to 7 slides. Try to, for every step in this particular algorithm, you first have you can go through all these slides again and again as I am doing right now, and it will be quite easy for you to understand what is happening here. Okay, so may I recommend you, if you haven't seen these two lectures, the past lecture and this lecture in a one go, I I highly recommend you to please go through that particular lecture again so as to refresh what I am talking here. Okay. Now the last topic in this topological ordering is what is the complexity. As you can easily see, for first we have to calculate the degree of each and every vertex. So the order will be O n, and for every step after the deletion of a particular vertex, we have to go through each and every remaining vertices again to recalculate their degrees. So practically, your order of time complexity amounts to O n square for adjacency matrix. But then again, if you are using an adjacency list, your order of complexity will amounts to O n, big O notation n actually. So this is what we have for topological sorting or ordering. Now we'll move on to our next topic, the stipulated topic for this particular lecture called Zastra's algorithm. Okay. Wait a minute. Just a second. So I'll not conclude this particular topic in this lecture as it's going to take me uh, amount time amount of more than 30 minutes. So I will split this particular topic in two halves. We'll talk some initial concepts here in this for the remaining time of this lecture, and we'll go through the actual algorithm in next lecture. Okay. So again, you have for understanding the Zastra's algorithm, you have to go through this lecture and next lecture in continuation. I recommend you that. Okay. So let's move on. Now, until now, all the graphs that we have seen doesn't have edge weights. That means we have seen the cyclic graphs, we have seen the acyclic graphs, we have seen the directed graphs, we have seen the non-directed graphs, but we haven't seen any of the edges that amounts to some weight. The weight means the cost of getting from vertex A to vertex B if there is a valid edge between them, or if there is a valid relationship between vertex A and vertex B. Now, how could a weighted graph can be of use for the example of day-to-day life that we have taken from the beginning of for the beginning of the graphs topic? Let's see that example again, or let's recall that particular example again. While calculating your flight routine from airport A to airport B, it is not only of your concern that if there is a route, or if we can figure out a route between airport A to airport B, we are also concerned with the cost. So let me again say that uh, suppose we have to go to from Delhi to Mumbai, and let's suppose in any way there is no direct flight from let's say Delhi to Mumbai, but your system or traveling agency's system which has implemented a let's say a graphical data structure for figuring out the path, devise a air route for you which starts like from Delhi to, let's say, Hong Kong, and then to New York, and from New York to, let's say, London, then Istanbul, then Dubai, then to Mumbai. Yes, there's the air route or the flight plan for your Delhi to Mumbai travel is valid, and it is quite possible that you might take it. But again, you also have to keep in mind that it's going to be too costly for you. Okay, that is not feasible in practical life. That is not feasible. The normal fare for New Delhi to Mumbai in common times is around 3,000 or 3,500. But if you go on through from Delhi to Mumbai, if there is no direct flight from the route that I have just told you, from that is from, let's say, New Delhi to Hong Kong, then to New York, then to London, and then Istanbul, Dubai, and Mumbai, it's going to cost you around 4 to 5 lakh rupees. So it's an enormous amount, enormous increase in the feasible amount that would have been if a normal flight there would be from New Delhi to Mumbai. So you have to keep in mind the feasibility of the problem also, if that particular problem is practically feasible cost wise or not. So this is that particular factor, the cost, that we haven't seen that yet in our problems. We haven't added that factor in our problem solution yet, but now we are going to add that particular cost factor into our problems so that we can find out a very practical and feasible solution for any kind of problem that could be implemented by the help of graphs. We have given you some of the practical examples. Let's say ticket price for the flight sector, tolls on the highway segments, distance traveled between the two stations, or typical time between two locations during peak hour traffic. All those things could be solved or efficiently or can be optimized. The solutions can be optimized by using the edge weights, by adding the edge weights to the graphs. Now, if a graph has weighted edges, in that case, we have to find the shortest paths, because shortest paths will always leads to, let's say, the lower cost. Okay, because the cost of getting from a particular vertex E1 a particular vertex V naught to particular vertex Vn depends on the edges that you have taken from getting on from V naught to V1, and then at the end of the after we have devised a path from V naught to Vn, we have to calculate the cost, and cost will be the addition of the weights of the edge E1 plus E2 and plus En, if all those edges are taken as the possible route of that your algorithm has devised from getting from V naught to Vn. So what we have to do is we have to find the shortest path from V naught to Vn such that your cost could be minimized. So in principality, the main factor that you have to that you have to keep in mind while devising an algorithm to find the shortest path from a particular vertex V naught to particular vertex Vn is that the cost should be minimum from getting from V naught to Vn. Okay, that cost factor will decide if a particular path is shortest or not. Not. That is what I am trying to say. So here we have an example. What I am trying to say here is, now this particular graph is a weighted graph. As you can see, I have named all the vertices as 1, 2, 3, 4, 5, 6, 7, and for all the possible edges or the valid edges, I have marked them with some weights. So the edge between the vertex 1 and 3rd has been weighted as 80, and edge between vertex 1 and 2 has been weighted as 10. As you can see, if we have to travel between, let's say these are the airports, and if we have to travel between the airport 1 to airport 3rd, so there are two options how your algorithm, if there are no weights, there we have two options with us. Your algorithm could find a path from 1 to 3rd directly because we have a valid edge, and we could also figure out a route from airport 1 to airport 2, and then airport 2 to airport 3rd. But after adding, let's say adding the weights, we can figure out that getting from airport 1 to airport 3rd directly would cost me, let's say, 80 bucks. And if I take the route from the airport 1 to airport 3rd via the airport 2, it would cost me only 16 bucks. So this particular route has much less cost added to my fare as compared to this particular route, that is getting from airport 1 to airport 3rd directly. So in terms of shortest path, I would say the path 1, 2 and 3rd, that is getting from 1 to 3 via 2, is the shortest or is short as compared to getting from the airport 1 to 3rd directly. So shortest path doesn't mean we have a direct connection. What it means is the term shortest will be assigned to that particular path which amounts to the lowest cost. Okay, so I think get the video is getting too long. Yeah. So I will end this lecture here, and in the next lecture we'll try to conclude the Zastra's algorithm, and we'll see how the shortest path analogy can be used to develop a efficient algorithm for finding such solutions for such kind of problems. Okay, thank you.